do not be scared of statically indeterminate beam deflection problems. They're a lot easier than they look as long as you can use superposition. As long as you can find all of your loading in the beam deflection tables, then this problem's going to be really straightforward and a lot easier than you think. So how do I know that this is statically indeterminate at all? Well, it's because there's 4 unknowns. You can only have 3 unknowns for a beam, which is usually a pin and roller or a single fixed joint, like a cantilever beam. So this has like a pin and roller simply supported with an extra loading in the middle at B. That makes it statically indeterminate. You cannot solve for all the reaction forces only using statics. We're going to also have to use the beam properties and basically find a compatibility equation based on the curvature of the beam to help us get another equation. In order to solve this, we're going to look. So your TA Serenity loves superposition tables. And so your first thought is this beam most similar to a cantilever beam or a simply supported beam? Because that's going to choose which tables you get to use. So for us, this is most like a simply supported beam with an extra piece in the middle. So first, we're going to ignore that roller joint in the middle. We're going to treat this like a simply supported beam with a rectangular distributed load on top, a single point force on top, and we're going to replace B, the roller joint, with an extra force pushing upwards on the bottom. So we're treating this like a simply supported beam, pin and roller joint with 3 different forces: distributed, point force, point force. When we go to the beam deflection tables, we're going to have to grab the equation for the entire elastic curve. Because we're not interested in deflection, say, in the middle of the beam or directly under the 125 point force, we're interested only in deflection at a specific point, point B. So we're probably going to have to plug in a position X. So we need the whole curve that is a function of X, so we can plug in our X equals 1.5 to find displacement at a specific position, not wherever the loading would have the maximum deflection. All right, so I got my tables, I got my 3 equations written down, 1 for the distributed load, and then 2 for the point forces. Now, the way I'm going to be using these is via a compatibility equation. I know that from all 3 of these forces pointing in all these different directions, the deflection at point B has to be 0 because there's a roller joint there. So however much the distributed load pushes B down, and the 125 is going to push B down, the force at B has to push it up to exactly cancel out those 2 other deflections. So if we add up V, if we add up deflection at point B for all 3 forces, that has to add to 0 because we know the beam is touching the roller joint at that point. So V1 plus V2 plus V3 equals 0, all the deflections at 1.5. So let's start plugging in numbers. For the distributed load, we're writing the 60 as 60,000, converting kilonewtons to newtons. We want all of our units to be in terms of newtons and meters so that we don't have to worry about unit conversions at the end of the problem. We'll do them all at the beginning of the problem and get regular normal units. X is 1.5, that's the point B that we're interested in. Length is the full length of 7.5. And I'm going to wait on EI until the end. For the 125 point force, again, I'm converting that to newtons, so 125,000. Now, B is the distance of the beam past the force. So B is the 2.5 at the far right side of the beam. The L is still 7.5 and X is still 1.5. That's our point of interest, 1.5 to B. And again, I'm going to save EI for later. Now for force B, we don't know what force B is, right? That's one of the final answers we're solving for, so it's still an unknown in the numerator. But lowercase b from this table, this equation, is now going to be 6 for this point force. Again, B on the drawing, that's all of the distance further past the force, the rest of the simply supported beam. So we got lowercase b of 6 for this version. but x is still 1.5. That's still the point up from the left side to b. And now you see the reason that I waited for EI is because there's EI in the denominator of all three terms in this equation, so it cancels out. If I just multiply everything by EI, it disappears. All right, so now just a million terms to type into the calculator. FB, 546,000 newtons, 546 kilonewtons. And now with FB known, it's not statically indeterminate anymore. Now it is statically determinate. We can just draw a free body diagram and solve for FA and FD. And when I draw my free body diagram, it looks to me like FA is actually going to be pointed downwards. That is, if B to D is going to be a big smiley face shape, then actually the beam probably wants to bend upwards to A. So pin A is probably actually holding that piece down. So I'm going to guess downwards at FA. We'll see if I'm right or not. But we'll keep you in suspense on that because first I'm going to do a sum of moments at point A, which cancels out FA and just uses the 546, the 60 times 7.5, which is the distributed load, just the area of the rectangle, the force of 60, and then the length of 7.5, 125 down, FD, leverage arms for everything. FD 199.1 kilonewtons, or 199,100 newtons, but I guess I'm in kilonewtons on this drawing. So sum of forces in the y direction equals 0, negative FA, since I assumed it's downwards, the 546 up, and then the other forces down, the 199 up, FA 170.1 kilonewtons, and it says positive, which means that my guess was correct, that FA actually is pointing downwards to hold that end down from the big smiley face from everything else pushing down and B pushing up. All right, it's TA Serenity. Before you go celebrating us being done, solving for the reaction forces, there's a second part to this problem. Find the maximum bending stress. So bending stress, this is the Flexure formula. My over I equals sigma, normal stress. So if I look up the properties of this I-beam, it's 617 millimeters tall, and it's based on symmetry, right? The centroid will always be right in the middle. So this value y, the distance from the neutral axis to the very top of the beam, or to the very bottom of the beam, will just be half of the total height. So 308.5 millimeters, or 0.3085 meters, so that's y. And now I can also get, just by looking this up in the table, 0.0012 meters to the fourth. So the last piece to be able to solve for stress is to find m, the moment. So to do that, you need a shear and moment diagram, and we need to find where is the maximum moment on this beam. All right, so the force at A is pointing down, so we go straight down 170. Because of the rectangular distributed load, it's just going to be sloping downwards at that slope of 60. So over a horizontal distance of 1.5, I'm going down 1.5 times 60, so I'm going down 90. That gets us from 170 to 260. But then I've got an upward force of 546 at B, so straight up at B to 200 and whatever, 286. Sloping downwards again at 60. So now this middle distance of 3.5. So we're going down 210. So this takes us to 76. Straight downwards 125. So that gets us to negative 49. It's still sloping down at a slope of 60. Distance of 2.5. So that takes us down another 150. 60 times 2.5 gets us to negative 199, which is good because the force over on the far right-hand side is plus 199, takes us back to 0. That's how you can double check that your shear and moment diagram is correct. You should always start and end at 0. If you end up somewhere not 0, that means you've made a mistake somewhere. All right, moment diagram, not going to be nearly as easy because all these diagonal lines, right? Horizontal lines, not too tough. Diagonal lines, harder. We still know we start at 0, a negative slope that gets even steeper. So we're going to come down to a cusp. But then we have a positive slope that becomes less steep, right? 76 is smaller than 286, so we'll start off steep and get less steep. So positive slope that becomes less positive. And then from there, where it drops from 76.49, now we have negative area. So now it's decreasing with a steeper slope. So it's still going to be concave down back to 0. So this gives us two candidates where the maximum moment could potentially be. It's either at the negative cusp or the top of that peak. One of those two positions will be the maximum. So we just need to find the two values there. So to find the value at the cusp, I just need to get the area of this trapezoid on the left-hand side. So the area of the rectangle is 170 times 1.5. And then the area of the triangle right beneath it, because I'm taking this trapezoid, turning it into a rectangle triangle. The area of this triangle is still a base of 1.5, height of 260 minus 170. So 1/2 base times height gives us another 67.5. So add this together, 322.5. That is the magnitude of the moment down at that negative cusp. Now, I'm going to ignore the trapezoid in the middle and instead solve using the trapezoid on the right-hand side. So the area of that rectangle is height of 49, base of 2.5, and then the triangle still has base of 2.5, but the height, 199 minus 49, so 1/2 base times height. Add the area and the triangle, add the rectangle and the triangle together, we get 310 as the height, basically meaning from the right-hand side is 0, it come up 310. So 322.5, that's the maximum. 310 was pretty close, but 322.5. So I can plug that in for M, multiply by Y, divide by I. So finally find the maximum stress in the beam, which will be at point B, because that's where the maximum moment is, 88,000 kilopascals. Now, why are we in kilopascals? Because again, I was lazy and did not convert my forces to newtons. This like 170 and the 125, these were all in kilonewtons, not newtons. I should have done like 170,000, 125,000 to get them in newtons, but I forgot, but I remembered. So 88,000 kilopascals, so 88.8 megapascals, maximum stress, statically indeterminate beam deflection problem solved by superposition. Thank you so much for sticking around to the end. Don't forget to hit the thumbs up button. Down in the description, there's a link to my full video playlist. Your TA Serenity's out of here, so you probably want to leave too. Have a great rest of your day. Good luck on your next test.